For Co-21A?
Oh,
I didn't think so. Looked a little lost. Or 17A? We're not here for Co-21A, we're here for Co-17A. Maybe I'm a little lost. All right. All right. We've got essentially 2 weeks left. We've got 2 days this week, 2 days next week. Same here. Action classes as well, right? For Monday, Wednesday, Friday. You meet this week, Wednesday and Friday. You meet next week, Monday and Wednesday. No class on Friday next week. Finals start on Friday, I believe. So no class on Friday, last class on Thursday of next week. As far as what's left for us to talk about in this class, there's kind of 3 main things. Graphing, which is kind of a big topic. It includes a lot of moving pieces. And then after that, optimization, which kind of feels similar to related rates in that it's a lot of setting up a problem and then doing the algebra or the calculus. And then finally, L'Hopital's rule. So those are kind of the 3 main topics we have left to talk about. We're going to talk about graphing today, and there's kind of a lot of things involved with graphing. So before we get there, we should probably talk about how to find relative maxima and minima. So how to find relative, also known as local, maxima and minima. Let's start off with a very straightforward example. Let's say our function is f of x equal to x squared, which is our kind of prototypical looking parabola, has a vertex at the origin, just like this. And we'll find a few things about this and kind of talk about it. So let's talk about finding the critical points first. I suppose, admit I'm going a little out of order here, and that usually for any function, if I was actually graphing it, I would first find the y-intercepts and the x-intercepts, and then I'd probably start finding the critical points. But this one, we kind of skipped that part. So to find critical points, we're going to set the first derivative equal to 0. So the first derivative is 2x. We're going to set that equal to 0, and we're going to get x equal to 0. And now the next part is how to classify that critical point. It could be where the function has a relative maximum or a relative minimum, or neither of those two. You could not have anything in a critical point. You could have, well, we'll see in the next example actually how you could not have either. So at this critical point, here's what we're going to do. And there's a couple different ways of finding out what's happening at a critical point. I'm a fan of what's called the first derivative test. So the first derivative test basically says the following. If you look at your critical point, which we're going to put on the number line here, there's our critical point of 0. We're going to look at what's happening to the first derivative on either side of that critical point. So on the left side, well, if I pick a number less than 0, like -1, and plug it into my derivative, we can see here that f prime of -1 is -2. I don't really care about the value. I just care about whether it's positive or negative. So over here, my first derivative is negative. Similarly, over here, if I plug in, say, +1, f prime of 1 is +2. What that means for us is that if your function has a derivative that's negative, that means the actual function itself is decreasing from left to right. Similarly, if the derivative is positive, the function is increasing. And if our function goes from decreasing to increasing, that means at that critical point, we have a relative minimum. So we have a relative minimum at x equal to 0, which I imagine you can all see on the graph. If you look at this graph here, at the point where x is 0, y is also 0, that point certainly is lower than any other point next to it. I'll also mention it happens to also be a global or absolute minimum as well, but we're not worried about that right now. We just care, is it is the local minimum, is it lower than all the things immediately next to it? And it is. What else to say about this here? We could also point out that if you're asked, f of x is decreasing on the interval from negative infinity to 0, because everywhere left of 0, the first derivative is negative, and f of x is increasing on the interval from 0 to infinity. Yeah, we should probably talk about that. So when I think about graphing a function, here are the things we usually look for, or we usually want to find. So when graphing a function, we typically include x and y intercepts, vertical asymptotes, and horizontal asymptotes. I mean, all of these with the caveat that if there are any, right? Your function could not have a y-intercept, or not have an x-intercept, or not have a vertical or horizontal asymptote. But if there are any defined, we find them. And then we're going to look for any relative extrema, meaning looking for relative maxes and mins. I will also mention here that this part of the problem where you find the relative extrema by looking at the first derivative's number line. So you're going to look at the number line for the first derivative. That actually tells you a lot about the shape of the graph. If you look back here at the work we did before, you say, oh yeah, we knew that left of 0, the graph was decreasing, and right of 0, the graph was increasing. So we had a vague idea of the shape of the graph just from looking at that first derivative sign chart. And that is always going to be the case. Whenever we're looking at the first derivative sign chart, it's going to help us see the kind of shape of the graph. And then I'll also point out, which we didn't do in this problem, but we will do kind of moving forward after we talk about it, is we're also going to find points of inflection, which is where we're going to use the number line for the second derivative. So I will say additionally, the number line for the first derivative tells us the intervals where the function is increasing or decreasing. And similarly, the points of inflection, the number line for the second derivative, tell us where the function is concave up or concave down. So what does it mean to be concave up or concave down? Well, there's a rhyme that's kind of lame, but I remember it. So someone said to me one time, concave up like a cup. Like a cup like that, and you like draw a little something. Or concave down, you might be able to guess this next one, like a frown. Again, not the most innovative, but hard to forget. So when a function is concave up, we think of it as opening upwards. When a function is concave down, it is opening downward. So certainly looking at that last function, it's concave up, right? It's certainly opening upwards. Let's talk a little more about concavity just so that we know what it is before we do any more graphing problems. So let's talk about concavity. And we're just going to get very general for a second. I'm not even actually going to draw, I'm not going to pick a function. I'm just going to draw something that is clearly concave up. So this function that I've drawn, which looks like the parabola we just talked about, but isn't necessarily, this function is concave up. But there's a few other ways of saying this that mean the same thing, which I want you all to be aware of. So let's look at some of these tangent lines for a second. So if I draw a tangent line over here, the slope of that line is really, really, really negative, right? It's almost vertical, but not quite, but it's certainly going down from left to right. Sorry, from left to right. And then as we move to the right, the slope of my tangent line is still negative, but it's less negative. If we keep moving to the right, slope is 0. And then further right, the slope is slightly positive. And further right, the slope is more positive. So throughout the whole period of being or interval of being concave up, it also looks like the first derivative, aka the slope of the tangent line, is increasing. Right? It was super negative, got less negative, so it increased to being less negative, and then increased to zero, increased to slightly positive, increased to more positive. Okay, so let me ask you all a question without looking over here for a second. It was just easy, you don't have to look at it, but if a function is increasing, getting bigger from left to right, what's its derivative? Is it positive or negative? It's positive. So if a function's increasing, its derivative is positive. Cool. So if this function is increasing, its derivative is positive. In other words, the second derivative is positive when the first derivative is increasing, when the function is concave up. So all three of these things really mean the same thing. It's just a different way of saying it. Either the function is concave up, or the first derivative is increasing, which is not usually the way we say it, or the second derivative is positive. Also, I learned this maybe a year or two ago. I thought it was kind of neat. For any function that's concave up, any tangent line that you draw, which we've drawn quite a few of them there, tangent lines are below the graph. And in a second, we'll see for concave up, kind of all the opposite things are, sorry, for concave down, all the opposite things are true. So if we look at one that's concave down, there you go. Similar ideas. Here, the function is certainly opening downward. And we can certainly look and see, yeah, any tangent line we draw, well, that's super positive. And then if we move to the right, less positive, 0, negative, more negative. So as we move from left to right, we're getting smaller in value. So we can say that our first derivative is decreasing. And when a function is decreasing, its derivative, in this case, the second derivative, is negative. And then here you can see also the tangent lines are above the graph. So when I graph a function, or when I ask someone to graph a function, usually I want them to include all these things. Not all these things, but all the stuff we listed on the previous page. The intercepts, the asymptotes, the critical points, and the inflection points. And I don't think we really need to list the intervals of increasing, decreasing, or concave over concave down, but they will be apparent to us based on our sign charts to find the other things. So let's look at a relatively straightforward example of how to graph something, including kind of all the stuff that we need to include, that's in that problem. Sure, we'll look at that one first. Let's look at f of x equal to, sure, x cubed minus 3x squared. We're going to graph this. But first, we're going to find all the things. Well, all the things which are to find. So, part 1, intercepts. Not too terrible. To find the y-intercept, we're going to set x equal to 0. So we're going to get f of 0 equal to 0 minus 0, which is 0. Usually the y-intercept is pretty not terrible. For the x-intercept, it requires a little bit more work. We have to set the function equal to 0. So x cubed minus 3x squared equal to 0, and it's almost always in our interest to factor as much as possible. We factor out an x squared, we're left with an x minus 3. So our x-intercepts are both x equal to 0 and x equal to 3. Normally, next we talk about asymptotes, both vertical and horizontal, but this has no asymptotes. And any polynomial, where it's just nice positive integer powers of x, will not have any asymptotes. So that's true for any polynomial. All right, and then we like to move on to what I usually refer to as the first derivative stuff. So we're going to find the first derivative, we're going to find the critical points, and then we're going to find the sign chart telling us where the function is increasing and decreasing. So the first derivative stuff. So my first derivative is going to be f prime of x equal to 3x squared minus 6x. We're going to set that equal to 0. And why? Well, we set it equal to 0 to help us find critical points, but also because knowing where it's equal to 0 means that we know that's the only place it can change from being positive to negative. So it's also going to help us kind of figure out the sign chart and where things are where the derivative is either positive or negative. So we're going to factor this. It's 3x times x minus 2 equal to 0. So my critical values are x equal to 0 and x equal to 2. So we're going to put those on a sign chart for the first derivative, which I had a little bit more room here. I guess I'll put it up here. So go up here, make our first derivative sign chart. And on that sign chart, the only things you want there are your critical values. You don't, so I would just say if 0 isn't a critical value, which it is here, but if it isn't a critical value, you shouldn't include it. We know where it is, but we don't need to write it down. So all we're writing here are the critical values 0 and 2. And we have f prime over here. And now our job is to pick things in each of these 3 intervals to see whether or not the first derivative is positive or negative. So pick something like, maybe it's helpful to write this up here. F prime is 3x times x minus 2. So we pick a number larger than 2, like 5. It's a positive times a positive, so the derivative is positive. Which means my function is increasing in that interval. Between 0 and 2, pick 1, positive, negative. The whole thing's negative, so it's going to be decreasing on that interval. And finally, over here, left of 0, we could pick negative 3. That's going to be a negative times a negative, which is positive overall. And so our function is doing that kind of deal. We know it's going to be increasing and then decreasing and then increasing. That also means we know where some relative extrema are. So at x equal to 0, well, our function went from increasing to decreasing, so we have a relative maximum there. Now, typically, when we find a critical point, whether it's a max or min, we usually like to find the x and the y coordinates so we can graph it and kind of know them. But fortunately here, we already know that if x is 0, y is 0, because if x is 0, that's our y-intercept. So that's going to be at the point 0, 0. And similarly, at x equal to 2, well, not similar, actually oppositely, at x equal to 2, the function went from decreasing to increasing, so it's going to have a relative minimum. And now we should plug in 2 to our original function to find the y value. So f of 2 is 2 cubed minus 3 times 2 squared, which is 8 minus 12, which is negative 4. So we get the point 2 comma negative 4. Usually at this point, you have most of the information you need to really graph the function. We're still going to find the second derivative information because it's typical, but I would kind of bet we could probably graph this thing pretty well right now. But let's go ahead and find the second derivative stuff. So we're going to take our second derivative. Also, for the second derivative, I point out that even though I factored the first derivative as 3x times x minus 2, I'd rather use 3x squared minus 6x to take the derivative of that. So my second derivative is going to be f double prime of x equal to 6x minus 6. If you like, you can factor out a 6 and say it's 6 times x minus 1. We're also going to set that equal to 0. We're going to find what I usually call critical points for the second derivative, or potential inflection points. So we set that equal to 0. We're going to get x equal to 1. We're going to draw the second derivative number line, so f double prime here. There's x equal to 1. Notice how I'm not putting 0 on my number line because we don't need to, even though we really want to. Pick a number larger than 1, like 2. My second derivative is going to be positive. Pick a number less than 1, like 0. My second derivative is going to be 0 minus 6, which is negative. So what that means for us is over here, left of 1, the function should be concave down. And over here, right of 1, the function should be concave up. And I know we haven't talked about this yet, but since the concavity changes at that point, x equal to 1, x equal to 1 is an inflection point where the concavity changes from one way to the other way. So here we have an inflection point at x equal to 1, and the y value would be f of 1, which is 1 minus 3, which is negative 2. So our inflection point's at 1 comma negative 2. We have more than enough information to graph it at this point. So now we're going to graph it. And I could probably squeeze it in here, but let's draw a larger graph so that we can make it look nice. Sorry, I'm covering stuff up, I know. So let's see. Let me start plotting things. So I have an x-intercept at 0 and at 3. I will point out, oftentimes for these graphs, my x-axis is usually pretty like the same most of the time. Sometimes my y-axis will vary wildly depending on how big the y numbers are. But don't worry about making your y-axis like to scale. It's usually not going to be. So let's see. I've got my x-intercepts at 0 and 3, and my y-intercept at 0. No asymptotes or intercepts. My first derivative stuff I have, let's see, I had a critical point at 0, 0. That's a relative maximum, so it's going to be something kind of like that right there. And at 2, negative 4, I can probably draw that to scale. I have a relative minimum. So it's going to be going like that. And I'm not going to worry about trying to draw any of the inflection point second derivative stuff at all. I'm just going to draw the graph using this first derivative information, meaning I know that my graph is going to be increasing until I get to 0, 0, decreasing from 0, 0 to 2, negative 4, and then increasing after that, making sure I go through that point 3, comma 0. So it'll look kind of like this. Yep, that's not the best, but you know. That's why it's not a good idea to draw your points on the x-axis until after you've drawn it. Could be better. So there's my graph with my relative maximum, right? That point is higher than everything next to it, and my relative minimum at 2, negative 4. And then although it looks a little bit wonky, here's my inflection point right about here at 1, comma negative 2, where the graph goes from opening downward to opening upward. And I've not drawn it amazingly well here, but that's kind of the idea. I will also say, so for our inflection point there, this is a point of interest. At the inflection point, the tangent line goes through the graph. Because on one side, it's concave down, where the tangent line should be above the graph. On the other side, it's concave up, where the tangent line should be below the graph. So if you tried to draw a tangent line right there, it would be on top over here and below over here, although I've not drawn that very well there, so it doesn't really, it's not very easy to see that that's happening the way I've drawn it. But that's kind of something that I usually think about when I'm thinking about my inflection point. It's where you have kind of a tangent line that goes through the graph. It's also where your rate of change either maxes out or bottoms out, right? Here, we're essentially decreasing as quickly as possible because our slope is as negatively steep as possible. And then after that, we come out and start being less steep. So we're not decreasing quite so fast anymore. Question? That was from the, we look back at our first derivative stuff. We had a critical point at x equal to 2, and then we plugged into the original function to get the y coordinate of negative 4. Yeah. Yes, excellent question. So finding an inflection point is a lot like finding a relative maximum or relative minimum. You're finding where instead of the first derivative being 0, you're setting the second derivative equal to 0. And then in addition to the second derivative being 0, the graph, the function also has to have its concavity change. Now, there's a difference here that I want you all to be aware of. For a relative maximum, the first derivative has to go from positive to negative, from left to right. For relative minimum, it has to go from negative to positive, left to right. For an inflection point, the order doesn't matter. It's an inflection point whether it goes from concave down to concave up, like it did here, or if it was concave up to concave down from left to right. Either way, we still just call it an inflection point. Good questions. So that's kind of the whole deal. It just so this is kind of one of the easier examples because there's not a whole lot going on with it. Let's look at something a little bit funkier. Unless there's any more questions about this. Sure. We'll look at a funkier one and then an easier one. So let's go ahead and look at this one. F of x equal to x over x minus 1 squared. It's going to be fun. Maybe. I'm going to change up a little bit, though. Let's say it's x plus 2 over x minus 1 squared. So make it a little bit more interesting. Probably the death of me with. So first things first, if we're asked to graph this thing, it's going to be a bit of a process. We're going to find the intercepts. So y-intercept, we said x equal to 0. We're going to get f of 0 is going to be 2 over negative 1 squared, which is going to be 2. Great. X-intercepts. Set the whole thing equal to 0, or set y equal to 0 if you want to think of it that way. Now, when we set a rational function equal to 0, the shortcut is just to set the top equal to 0. Because really what we're doing is we're going to multiply both sides by the denominator. If we multiply the left-hand side by x minus 1 squared, we're going to get x plus 2. If we multiply the right-hand side by anything, we're still going to get 0, because 0 times anything is still 0. So we're really just, in essence, setting the top part of that quotient equal to 0. So we get x equal to negative 2. So that's our x-intercept. All right, we do have some asymptotes defined here. So for vertical asymptotes, that's where you might be dividing by 0, essentially. So to find vertical asymptotes, I'll say with one exception, it's usually when you have a rational function, you're just going to say, where is the denominator equal to 0? So we're going to set x minus 1 squared equal to 0, and we're going to get x equal to 1. Just in case you're curious, the exception to what I just said is that if you have a logarithmic function, logarithms also have vertical asymptotes, but it's not because you're dividing by 0, it's that's how the logarithm works. Horizontal asymptotes are a little bit more interesting. I'll point out when we get into some later examples, the horizontal asymptotes might require use of L'Hopital's rule. For now, we're saying, well, we're really asking what's happening as you go way out to the left or way out to the right. In other words, we're asking what's the limit as x goes to infinity of x plus 2 over x minus 1 squared. This is kind of taking us back to like week 2 here, where we talked about limits to infinity. And we talked about limits where you had a quotient on top and thing on top and the bottom. And what really, really mattered was how the degrees of the top and the bottom compared. The numerator, the degree is 1 because we have x to the first. The denominator, the degree is 2. If you multiply it out, you get x squared minus 2x plus 1. So since the denominator has a larger degree, this fraction is going to get smaller and smaller and smaller as the inputs get larger and larger and larger. This is going to end up equaling 0 because the degree on top is less than the degree on the bottom. We don't really want to do all the work of dividing everything by x squared and then seeing what the limit is. We're just going to use the tricks we've learned from previous weeks. All right, we've done all of the original function stuff. Now we're going to move to the first derivative. Here it is going to be a little bit gross to find this first derivative. So first derivative stuff. All right, so we're going to have to use the quotient rule here. So my derivative is going to be the bottom times the derivative of the top, which is 1, minus the top, which is x plus 2, times the derivative of the bottom, which is, I've got some stuff squared, so it's going to be 2 times my stuff to the first power times the derivative of the inside stuff, but that's just 1. All divided by x minus 1 squared squared. And definitely for problems like this, these do require some simplifying because we need to be able to kind of make this as easy to deal with as possible so we can figure out where it's equal to 0. So, yeesh. Here's something to note. And this, point out, this is always going to happen with the question. If your denominator starts off as having a power higher than 1, that expression is going to show up in both terms in your numerator where they're being subtracted from each other, and you can always factor that out from the numerator. A better way of saying that is that whenever you use the quotient rule, the power in your denominator is going to be one larger. So if my original thing started off with x minus 1 squared, after I do all the simplifying I can, I should end up with x minus 1 to what power? To the third. But I have an x minus 1 to the fourth, so I should be able to cancel one of those by factoring out an x minus 1 to the top. But that's something I would encourage you to remember, that whenever you're using the quotient rule, if you simplify enough, your denominator's power should have only increased by 1. So we should end up with x minus 1 cubed after we do the simplifying here. All right, let's do it. So I can factor out x minus 1 from here and here. And yeah, I'm not going to, yeah, sure. I'm not going to draw the graph on this page, so I'll just do this here. So x minus 1, factor that out. And then we're left with an x minus 1. And over here, we're left with a minus x plus 2 times 2. And the denominator, we have x minus 1 to the fourth. And now you can see, oh yeah, one of those x minus 1s cancels with one of those. Simplifying the insides, we have x minus 1, sorry, simplifying the stuff in the brackets, I should say. We have x minus 1 minus 2x minus 2 times 2 is 4. All over x minus 1 cubed. Finally, simplifying the numerator as much as possible, we get x minus 2x, so negative x, minus 1 minus 4 is minus 5, all over x minus 1 cubed. If you really, really wanted to, you could factor out the negative 1 from the top and write it as negative 1 times x plus 5, all over x minus 1 cubed. Plus. So, this is where things are going to get a little bit strange. If we set this equal to 0, what's the single critical point that we get? What's going to make this fraction equal to 0? Well, if we set the top equal to 0, we're going to end up getting x equal to negative 5. I really need to write the negative 1 right there, but yeah. That's our only true blue critical point. Now, you might observe that there's another value of x that makes this first derivative undefined, and that is x equal to 1. X equal to 1 is not a critical point because it's not in the domain of the original function, because the original function has a vertical asymptote x equals 1. That said, it's still a place where the sign of the first derivative can change, so we want to include it when we draw our first derivative sign chart. Any place where the first derivative is undefined or equal to 0, regardless of whether it's in the domain of the function or not. And sometimes it will be in the domain, like in the next example we're going to see. So don't just think it's always going to be not defined or not like something that's in the domain. It's just in this example, it happens to be that way. So here's our first derivative sign chart. And on my first derivative sign chart, I'm going to include a positive 1 and a negative 5. And then we're going to see what's going on. And maybe I should write out my first derivatives here. And my first derivative, just for reference, is negative 1 times x plus 5 over x minus 1 cubed. And just like every other time we do these sign charts, we pick a number and we see what the sign is. Now, I don't like to do, as you probably know, I don't do a lot of writing down when I pick this number. I just look at like what are the overall signs. So when I pick like x equal to 2, I'm like, cool, 2 plus 5 is positive, times negative 1 is negative, and 2 minus 1 is positive, so I have a negative divided by a positive, which is going to be negative overall. Between 1 and negative 5, I'm going to pick 0. I almost always pick 0. If 0 is a choice, it's usually a good choice. I'm going to pick 0. 0 plus 5 is positive, times negative 1 is negative. 0 minus 1 is negative, and the negative number cubed is still negative. So a negative divided by a negative is positive. Finally, picking something less than negative 5, like negative 6. Negative 6 plus 5 is negative 1, times negative 1 is positive. On the bottom, negative number cubed is also negative, so I have a positive over a negative, which is negative. You could also use the trick or observation that since 1 came from a factor with an odd power and negative 5 came from a factor with an odd power, the sign's going to change every time we cross from one important point to the other side of the important point. So we went from here to here, we changed, and from here to here, we changed. So that means our function is decreasing, then increasing, then decreasing. Okay, so at x equal to -5, since it was decreasing then increasing, we have a relative minimum. I'm not going to try to trick you. I'm just going to tell you at x equal to 1, even though it's increasing, decreasing, we don't have a relative maximum because the function is undefined there. We have a vertical asymptote. So what's probably happening at x equal to 1 is something like this. We have like a vertical asymptote. On the left side, sure, it's increasing. On the right side, it's decreasing. That's what's happening at x equal to 1. So you definitely have a change in the sign of the derivative there, so it's important to include that, but it's not going to be a relative extreme. It's not a relative maximum or a relative minimum because it's undefined. But if someone had asked you to say, give me the intervals where it's increasing or decreasing, you're going to miss something if you don't include this one on your sign chart. So it's certainly increasing on the interval from -5 to 1 and decreasing on the interval from -infinity to -5 union 1 to infinity. I don't usually include that information in my answer unless specifically asked to, because again, I think this sign chart says everything I just said without writing so much. Oh, and there's still one more thing to do here before we start talking about the second derivative. We have to figure out what f of -5 is, because if we're trying to plot all of our important points, we need the y value there. So plugging -5 back into the original function, our relative minimum is going to be, well, f of -5 is -5 plus 2 over -5 minus 1 squared, which is -3 over -6 squared. That's kind of gross. -3 over 36, which is -1/12. All right. Okay. Things do get messy when you're finding a second derivative and it's a quotient. It can't be helped. So let's go ahead and do the work of finding the second derivative here. And I would point out that even though I did factor it out the -1 here, I'd probably use this version of my first derivative to take the second derivative of. So we're going to remind ourselves here that our first derivative is -x minus 5 over x minus 1 cubed. And now we're going to find the second derivative stuff. Meaning where it's concave up, concave down, and if we have any inflection points. So, all right, second derivative. I'm like, how do I do this again? Second derivative. Okay, so it's again the quotient rule. Now let's be extra super careful here. It's the denominator times the derivative of the top, which is -1, minus the top, which is -x minus 5, times the derivative of the bottom, which is 3 times x minus 1 squared, times the derivative of the inside, which is still just 1. All divided by my denominator, x minus 1 cubed, squared. Okay, so quick question. Show me on your fingers. After I do all my simplifying, I'm expecting to have x minus 1 to what power on the bottom? Remember what I said about quotients before? How this has x minus 1 cubed here. I'm expecting my power to be 1 more. So I'm expecting to get x minus 1 to the 4th power after I simplify. But it's going to be some work. So let's see. So if I know that, well, I know right now I have x minus 1 to the 6th on the, x minus 1 to the 6th on the bottom. So that tells me also that I should be able to factor out an x minus 1 squared from the top, which I can. There's an x minus 1 squared right there, and there's more than enough of them right there. So if I factor out an x minus 1 squared, now I'm left with an x minus 1 there, times a -1, minus -x minus 5, times 3. I pulled out the x minus 1 squared, so it's not there anymore. So that's all I've got. All right, let's simplify. We got x minus 1 squared times, and distribute the -1 here, so I get -x plus 1. I'm gonna choose the minus sign here, so it's sure, it's plus x plus 5 times 3. So it's going to be plus 3x plus 15. All divided by x minus 1 to the 6th. We can cancel 2 of the x minus 1s. Simplify what's in the brackets. So I've got 3x minus x is 2x. I've got 1 plus 15, which is 16, over x minus 1 to the 4th. And if you like, and I kind of do like, I'm going to factor out the 2. You get 2 times x plus 8 over x minus 1 to the 4th. All right, so setting this equal to 0, because again, we're trying to find the critical point for the second derivative. We're going to get x equal to negative 8. That's our critical point for the second derivative. And then we also are still going to include on our number line x equal to positive 1 because it's where we have a vertical asymptote. Any place the sign can change, we have to include that. All right, so now here's our number line for the second derivative. I don't know why I'm writing second. I mean, f double prime. So we've got positive 1 and negative. You know what I've actually learned over the years is not a bad idea is on your number line when you do this, if you have a vertical asymptote somewhere, jar yourself in a little vertical asymptote. Like, oh yeah, there's a vertical asymptote there. I can't have a maximum or minimum. I think that helps. So let's see. Looking at our second derivative right here, if I pick a number larger than 1, the numerator is positive, and notably the denominator is always positive because it's raised to an even power. So positive over positive is going to be positive. Between negative 8 and 1, I'm going to pick 0. The numerator is still positive. The denominator is still positive, even though it's a negative number to the 4th power. And then finally, over on the other side of negative 8, like if I pick negative 9, negative 9 plus 8 is negative 1, so the numerator is negative. The denominator is still positive, so it's a negative over a positive, which is negative. So our function is looking like it's concave down, then concave up, then concave up. So it looks like we have an inflection point at x equal to negative 8. I guess we should find the y value. Y is going to be f of negative 8, which is negative 8 plus 2 over negative 8 minus 1 squared, which is negative 6 over 81. That's terrible. Which is negative 2 over 27. Fun times. So now putting it all together, right? Because it feels like we have a lot of information. So what I would say is when I'm graphing these things, I almost always ignore the second derivative information. Like it doesn't really help you draw the graph. But I'm definitely going to be looking at the stuff from the first derivative. So I've got my decreasing, increasing, decreasing. I know I have a vertical asymptote here. So it's going to look something kind of like that. So let's try putting on our coordinate system some intercepts and see what we can draw. Let's see. So let me remind myself what things were here. We had a y-intercept of positive 2. We had an x-intercept of negative 2. I need some, definitely leave myself some room on the left side here because I'll go all the way out to negative 8 here. 3, 4, 7, 8, 9, cool. So there's my x-intercept of negative 2. I'm going to get that a little more centered there, sorry. And then we had a vertical asymptote at x equal to positive 1. And we had a horizontal asymptote of 0, which I'm not going to draw because it's just my x-axis. And then our first derivative stuff gave us, we had a relative minimum at negative 5 comma negative 1/12. Okay. So over here at negative 5, we're very, very just slightly under the x-axis. So there's our relative minimum. And then from our second derivative, we did get an inflection point at negative 8 comma negative 2/27, which is a little bit higher up. It would have to be, right? If that's your minimum relative, right, it's going to be lower than that point over there. All right, I think we're ready to draw it. So I've got my my horizontal asymptote of the x-axis. So I know essentially I'm getting really, really close to that out here. I'm going to hit that inflection point. And then I'm going to hit this bottoming out right here, which again, probably should have waited to draw it. I'm going to go through that x-intercept. do that y-intercept. So just to show everybody what happened here, from negative infinity up to -8, and from here to here, we were decreasing and concave down. It's kind of hard to see the concavity there, but it is concave down, very, very slightly. Now from here to -5, we're still decreasing, but now we're concave up. And then from here to here, now we are increasing and concave up. And then after this, we're going to be decreasing and still concave up. So we're going to look like this. We don't really have any guide points to go through here, but we do know that we have a horizontal asymptote as we move out to the right of the x-axis. So we're just going to go like this. That's our graph. It's kind of a lot. Some of these graphs are kind of a lot. Now, one thing I'll say is that oftentimes when functions are this messy on an exam, sometimes they'll just give you the function in the first and the second derivative so that you don't have to, because they don't really care about the work of finding the derivative so much as being able to use the tools for graphing or graphing things. So sometimes when the derivatives are really messy, you will just be given them on an exam, depending on your instructor. Questions so far? All right, let me have you guys do one. Yeah, this one's not too terrible. So this one's more similar to the first one, but different. So the function is going to be f of x equal to x to the fourth minus 4x cubed. And I want you to find, well, I'll write out what I want you to find. Find the x-intercept. Sorry, first find the y-intercept. Then find the x-intercepts. There are no asymptotes. Find the first derivative. And set equal to 0 to find the critical points. Try to find all the things for this one. Intercepts, critical points, secondary critical points, et cetera, et cetera. Like another minute and a half to work on this before we start yet. All right, let's take a look. So a function is x to the fourth minus 4x cubed. To find and the y-intercept's not terrible here. It's almost never terrible. Plug in 0 for x, you're going to get 0. X-intercepts, we set the whole thing equal to 0. And we usually just factor right away. Also something just I'll point out, usually when you're finding the x things, it's better to have the function factor as much as possible. By the x things, I mean the x-intercepts and the vertical asymptotes. Usually when you find the y things, it's almost better to have the function multiplied out, like the y-intercept or the horizontal asymptotes. So here it's much easier to find the x-intercepts by factoring out x cubed. And we have x cubed times x minus 4 equal to 0. So we get x equal to 0 and x equal to 4. No asymptotes to speak of here because, again, it's a polynomial. We never have asymptotes for a polynomial. So we move on to finding the first derivative stuff. So taking our first derivative, it's going to be 4x cubed minus 12x squared. And we set that equal to 0. Well, let's factor it. Let's factor out of 4x squared. We're left with an x minus 3. And that's going to give us either x equal to 0 or x equal to 3. Now we're going to plot those on the number line. 0 and 3. Well, let's make up something interesting. Yeah. Okay. So pick a number larger than 3, like 4, it's positive. And now I'll point out the other way of doing this. Instead of keeping on picking numbers, see if it's positive or negative, I'm going to say, great, 3 came from this factor. That factor has an odd power, so the sign's going to change. 0 came from that factor. That factor has an even power. The sign is going to stay the same. So certainly at x equal to 3, we have a relative minimum because it's decreasing, then increasing. And at x equal to 0, we don't have a minimum or a maximum. It's neither. So we have a relative minimum at x equal to 3, and the y value is f of 3, which is going to be, if I look at the factored form here, 3 cubed times 3 minus 4, which is negative 27. So my relative minimum is 3 comma negative 27. And as far as whether this function is increasing or decreasing here, so I would say it's increasing on the interval from 3 to infinity, and it's decreasing on the interval from negative infinity to 3. So just a point of interest, if your function is decreasing, and it's defined at the point between those two places, then it's perfectly fine to say that it's decreasing on the entire interval. You just see, like I just included the 0 in the negative infinity to 3 there. That wouldn't be true if our function looked like this. Just as a quick aside, if your function looked like this, oh, sorry, y equal to 1 over x. Well, let's look at our derivative. Our derivative here, if y is 1 over x, which is x to the I know I'm going off to this tangent here. I'll promise to come right back. Our first derivative is -1 times x to the -2nd, or -1 over x squared. And I would point out that for any value of x except 0, that derivative is always negative. So y prime is always negative, except at 0. So here's our first derivative sign chart. 0, the function's undefined, the derivative is undefined, but on the other side, it's negative here, decreasing, decreasing. But if I was asked to talk about the interval where this was decreasing, the answer would be, well, it's decreasing on -infinity to 0, union 0 to infinity. Because we can't include 0 because the function isn't defined there. Whereas in this previous example, it's totally fine to include 0 because the function is defined there. So we're including 0 in our interval of being decreasing because it makes sense to. I know it's kind of a small, subtle kind of, we do it this way for this way for that. It's not a huge deal, but I just want to point it out. All right, so we've got our first derivative stuff. Let's graph it first. Let's not find the second derivative stuff just yet. So if we start graphing it, I know I've got a y-intercept at 0, 0, an x-intercept at 4, 0. And I have a relative minimum at 3, -27. This is where my y-axis is not going to be, there's the same scale as my x-axis. I'm going to say my relative minimum is going to be like down here. And so I have a pretty good idea of how this looks. It's going to come down this way. It's going to decrease. It's going to flatten out for just a moment, because at 0, even though it's not a relative minimum or relative maximum, it is the place where the derivative is equal to 0, which means the tangent line is horizontal there. So right there, it's going to look like that. And it's going to continue to decrease. And then it's going to bottom out and then increase like that. Whoops. Ooh, wow. Okay. Sorry. Got a little carried away there at the end. Here's my relative minimum at 3, -27. Now, let's go ahead and find the second derivative stuff. So for our second derivative, which is f double prime of x equal to 12x squared minus 24x, if we factor out a 12x, we're left with x minus 2. So we're either going to get x equal to 0 or x equal to 2. We'll put that on our second derivative number line. Well, if we plug in 3, positive times positive is positive. Plug in 1, positive times negative is negative. Plug in -1, negative times negative is positive. So our function is concave up, then concave down, then concave up. So we have 2 inflection points. We have an inflection point at 0. I'll say 0, 0, because we know the y value. And we also have an inflection point at 2, whatever f of 2 is. I guess we could plug it in. F of 2 is going to be 2 to the 4th, which is 16, minus 4 times 8. So 16 minus 24 is -8. So over here at 2, -8, that's where we have an inflection point. I know it doesn't look perfect because, I graphed it. But that's the place where the concave... So up here to the left is concave up, opening upwards, or as I would say, any tangent line I draw has to be below the graph. And over here, from 0 to 2, it's concave down. All my tangent lines are above. And then from 2 to onward, it's concave up again. All my tangent lines are below. And even though I'm not great at drawing it, right here, this inflection point, the tangent line would go through the graph. Above on the left, below on the right. Same thing here. The tangent line here, which is the x-axis, goes through the graph. Inflection points are kind of weird, but I'd like to point that out. What else to say about this? I feel like there was something else I wanted to say here. Oh, yeah, I know what it was. Okay. So one thing I will say is that when you find critical points for using your first derivative, if they don't end up being a relative max or relative min, it's not guaranteed, but they almost always end up being an inflection point for your second derivative. So it's good to keep an eye on those points that end up not being anything in your first derivative here. Okay, let me see. There's one more thing I want to say. Sorry, I keep thinking of like all the things I want to say. Oh, I know what it is. So let's revisit this problem just for 1 second. I want to say something else about this. So I'll say to find out that 3 was a relative minimum here, we use what's called the first derivative test. We just looked on either side of that function to see what the first derivative was doing, and either side of that critical point, see what the first derivative was doing, and that told us we had a relative minimum because we knew that we were decreasing on the left, increasing on the right. And I would say that for graphical purposes, the first derivative test is the best test to tell us if we have a maximum or minimum. However, there is another test you can use. It's not as good. There's also something called the second derivative test. But it's not about inflection points, it's about relative maxes and mins. So the second derivative test for relative extrema. The reason this test is a bummer sometimes is because it's not always conclusive. It won't necessarily tell you if every point is a maximum or minimum or neither. It'll either be a maximum or minimum or inconclusive, but it can be inconclusive for kind of any case. Your thing could have been a max or a min or a neither. So you really can't think. But here's what the test says. So if we have a critical point from the first derivative, from setting f prime of x equal to 0, we can see if it's a relative maximum. We can see if our critical point, let's call it C, is a relative max or min by plugging C into the second derivative. Because here's what's going to happen. If f double prime of C is positive, that means your function was concave up. But if your function is concave up and your first derivative is 0, meaning you have a horizontal tangent line, does that look like it's going to be a relative max or a relative min? Definitely looks like a minimum. So if your second derivative is positive and your first derivative is equal to 0, that means you have a relative minimum at that point. Similarly, if your second derivative is negative and your first derivative is equal to 0 at some C, then we can say that, oh, we're going to have a relative maximum. This idea is not super important in this class. This idea becomes super important in 17C when we start talking about how to determine relative extrema of functions of two variables. And this idea comes back roaring at you. But then the bummer is if your second derivative is equal to 0, we don't know. It could be literally anything. It could be a relative max or a relative min or an inflection point, or maybe even none of the above. So in that previous example, let me just point out how this would have worked. So in the previous example, we had our function, which was x to the fourth minus 4x cubed. Our first derivative was 4x cubed minus 12x squared. And our second derivative was 24x squared minus 24x. I feel like I'm making a small mistake here, but maybe not. Maybe I'm just silly. Let me just double check and see I'm not doing anything crazy. Nope, that looks totally like what we had. I see the mistake I made. Do you guys see it? It's in my second derivative. It should be instead of 24x squared, it should be 4 times 3 is not 24, it's 12. It should be 12x squared. Oh my gosh, it should be, my brain should work maybe? Yeah, 12x squared minus 24x. Sorry about that. And then setting this one equal to 0 gave us the critical points of x equal to 0 and x equal to 3. So now if we plug this into the second derivative, look what happens. F double prime, let's factor this as 12x times x minus 2. F double prime of 3 is going to be 12 times 3 minus 2, which is positive 36. So that means we know that at 3, the function's concave up, so 3 had to be a minimum. But kind of in a bummer way, if you plug in 0, you get f double prime of 0 is 0, which means it's inconclusive. So that certainly agrees with what the graph looked like, right? We can see at our graph, oh yeah, at 3, it was concave up and we had a relative minimum. And at 0, the second derivative was 0, so we weren't able to tell. So this is the second derivative test for experiment. It's not super useful for graphing. It is a lot more useful when we start talking about optimization, which is the next thing, where you're trying to figure out if some function modeling some sort of surface area or volume or something else of the object, if you're trying to either maximize or minimize that or some cost function, it can be often a lot easier to take the second derivative of your function, plug in your one critical point to see if you have a maximum or a minimum instead of trying to use the first derivative test for it. It's usually easier to use. So that's really why we're talking about this here. Yeah. So let me just show you one more thing about this and then we can move along. The reason this test is inconclusive is because, well, let's look at these two examples. Let's look at f of x equal to x to the fourth and f of x equal to x cubed. Both of these have a critical point at x equal to 0. Take your derivative here. The first derivative is 4x cubed. We set that equal to 0. We're going to get critical point of x equal to 0. Same deal here. I mean, similar in that you take your derivative, set it equal to 0. You're going to get also x equal to 0 as your critical point. And both of these, the second derivative test completely fails us. If I take the second derivative in either case, the second derivative here is 12x squared. And if I plug in 0, I get 0. Same deal here. My second derivative is going to be 6x. And if I plug in 0, I'm going to get 0. But these two functions don't have the same type of, what's the word I'm looking for, feature at the origin. This function, x to the fourth, looks like a really, really exaggerated parabola. So this function does have a relative minimum at 0, 0. Whereas this function, x cubed, is kind of your classic example of a function that has an inflection point right at the origin. So again, all I'm trying to show you with these two examples is that the second derivative test can be unhelpful sometimes. This doesn't tell us either way we have, whereas the first derivative test tells us a lot. If we look at the first derivative here, on the left side, the first derivative is negative. On the right side, the first derivative is positive. So we're decreasing, increasing, so we know we have a relative minimum. On the other hand, over here, although it doesn't tell us we have an inflection point, it tells us we don't have a relative max or min, because for my first derivative over here, my only critical point is 0, and if I pick a number on the left, the derivative is going to be positive. Pick a number on the right, the derivative is going to be positive. So this function is increasing, increasing. So we know we definitely don't have a relative min or relative max at the origin. And then if we took the second derivative set equal to 0 and then tested the concavity, we would find that we have an inflection point. Oh, it's a lot. So, yeah. So my opinion is I hate the second derivative test. I feel like for graphing, it's terrible because it's never going to be like, first of all, if you're graphing, you should be doing this anyway. You should be always, 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 if you're graphing, finding the first derivative, setting equal to 0, finding your critical points, and putting them on a number line so that you can see the shape of your graph, whether it's decreasing or increasing. This is probably the most useful piece of information when it comes to graphing anything, is what the sign chart for the first derivative looks like. Okay, let's look at one more graphing example because there is one other thing I want you guys to be aware of. Yeah, let's look at, sure, that one's not the worst thing I've ever seen, I guess. Let me double check. Let me look and see which one of these is not as bad to deal with. Sorry, one sec. Yeah, that's fine. Okay, it's not pretty, but it's good. So let's look at this function. We're going to graph f of x equal to x to the 4/3 minus 4x to the 1/3. I'll point out this is not a polynomial. We do not have integer powers of x, so we have to be a little bit more on the lookout for things here. So let's find the intercepts. Plug in 0. 0 to any positive power is 0, so we're good to go here. We get just 0. Setting the whole thing equal to 0. So x to the 4/3 minus 4x to the 1/3. It's definitely in our interest to factor out an x to the 1/3. So we factor out x to the 1/3 times x minus 4. We end up getting either x equal to 0, which should never be a surprise if y equal to 0 was one of your y-intercepts. X equal to 0 has to be a corresponding x-intercept. And then we're also going to get x equal to 4. So those are our intercepts. Also, I would mention that this function has a domain of everything, right? So even though it's kind of weird with these fractional powers here, you can always take a cube root of any positive or negative number. Same deal here, a cube root and then a fourth power of any positive or negative number. So sometimes it is worth mentioning what the domain is or is not. Our domain here is everything. Now let's look at the first derivative. Oh, no, sorry. But I skipped the asymptotes. Asymptotes. Are there any asymptotes? There aren't. How do we know? Well, there certainly aren't any vertical asymptotes because there isn't any division by 0 problems here, right? We don't have a fractional thing or a logarithmic thing, so there's definitely no vertical asymptotes. And if you look at the more factored form of this, if you look at your function as f of x equal to x to the 1/3 times x minus 4, you can probably convince yourself that there's no horizontal asymptotes either, because the horizontal asymptotes just ask, is there a number we're getting closer and closer to as x gets really, really, really big or really, really negatively big? There isn't here. Let's see why. If we take the limit as x goes to infinity of x to the 1/3 times x minus 4, well, the cube root of infinity is still really big. And infinity minus 4 is even bigger. And a positive big number times a positive big number is a positive big number. And similarly, if we go to the left, the cube root of negative infinity is negative infinity. And negative infinity minus 4 is still negative infinity. And a big negative number times a big negative number is a big positive number. So no horizontal asymptotes, because on either side, we're actually going to be going up, up, up to the left and up, up, up to the right. That's what we'll expect to see at the end. Okay, so now this is where things are going to get a bit messy. The first derivative stuff. So let's look at the unfactored version and take the first derivative. First derivative is going to be 4/3 times x to the 1/3 minus 4 times 1/3 is also 4/3, and 1/3 minus 1 is negative 2/3. And I'll say, whenever you see a negative power here, you should think we have to be extra careful, because 0 to a negative number is undefined. It's like division by 0. In fact, we already know here that 0 is going to be a critical point because it makes the derivative undefined. And I was looking at one of the class's notes. One of the teachers was talking about like finding critical points by setting the derivative equal to 0. And I feel like they were kind of ignoring the fact that you also technically have to check to see where the derivative is undefined. So when you're finding critical points, it's either where the derivative is 0 or where the derivative is undefined. You have to look for both. A lot of the time, you're not going to find any place where the derivative is undefined, but in this example, we will. So I'm going to factor. Factoring is our friend here. I'm going to factor out of 4/3 and always the smaller power of our common factor. So I have an x to the positive 1/3, I have an x to the negative 2/3. I'm going to factor out an x to the negative 2/3. So I'm left with, let's see, a 1 times x to the 1 minus a 1 times, that's all I got, just a 1. And if you're not sure, you can always multiply it back out to c. If you multiply the 4/3 times 1, you get 4/3. And the x to the negative 2/3 times x to the first, you add those powers, and negative 2/3 plus 1 is positive 1/3. And similarly, this times negative 1 is just going to be minus 4/3 x to the negative 2/3. Now, I wouldn't leave it like this. I would rewrite it as 4 times the parentheses over here, which is just x minus 1, over the 3 in the denominator, and I'm going to move that x to the negative 2/3 down to the denominator as x to the positive 2/3. Yeah, that is how I prefer to write that. Yes. I will also say, even though that's how we're writing it, we're definitely going to use this version of it to find the second derivative. All right, if we set this equal to 0, we're going to get x equal to 1 as a critical point. And if we also see where this is undefined, we're going to get x equal to 0. So we do have a critical point at 0, and it is an actual for real critical point, not like where we have a vertical asymptote, because 0 is in the domain of the original function. So this 0 actually is a critical point. So let's look at our sign chart here. Ooh, sign chart's going to be interesting. So we got 1 and 0. Pick a number larger than 1, like 8. 8 minus 1 is positive. 8 to the 2/3 is also positive. It's 4. And so we have a positive over a positive, so it's positive. Between 0 and 1. Well, let's think about 1/2. I don't know what 1/2 to the 2/3 is, but I know it's positive because the positive number to any power is always positive. Say it again, a positive number to any power is always positive. On the other hand, up top here, 1/2 minus 1 is negative 1/2. So we have a positive number we have a negative number divided by a positive number, so it's overall negative in there. And then left of 0, if we plug in negative 1, the top is negative, the denominator is positive. Because it's negative 1, it's the cube root of negative 1, which is still negative 1, but then we are squaring it. That 2 in the numerator is going to make all of the 2 in the numerator right there is going to make any input for x come out positive after we square it. So it's going to be a negative or positive, which is still negative. So we are decreasing, decreasing, increasing. So we have a relative minimum at x equal to 1. I don't think we have enough time to, yeah, fine, we have enough time. But let's actually go ahead and look at what our function looks like here, and then maybe we'll fill in the rest. So we know that we have the intercept of 0, 0 and 4, 0. We just found that we have a relative minimum of x equal to 1, and if we plug in 1 to our function, f of 1 is actually really easy to find. It's 1 to the 4/3 minus 4 times 1 to the 1/3, but 1 to any power is 1, so we just really get 1 minus 4, which is negative 3. So our relative minimum is at 1 comma negative 3. So right about there. And what's going on at 0? Well, 0, the derivative is undefined. If you have a function where the function is defined but the derivative is undefined, that usually means you either have a cusp, like a pointy point, or you have a vertical tangent, which is actually what we have here. So what's happening here is the function looks kind of like this. So we can draw it here. It's gonna get very vertical just for a brief moment there, and then it's gonna bottom out and then come back up this way. That's about what that looks like. There is, yeah, so I missed it, but there is also an inflection point over here where the concavity then changes to being upward like that instead of downward like it is. So there is some inflection point over here, which we don't have the time to find today, but we can talk about it next time. I will tell you the inflection point occurs at x equal to negative 2. So that's what, so you can have a function where you have critical point where the derivative is undefined, but the function is still defined. That happens sometimes. All right, I'll see you on Thursday. We'll talk probably more about graphing as well as we'll talk about optimization. Because optimization is then taking some actual like thing we're representing and trying to find where it has a relative minimum or relative maximum based on the equations we've come up with. It's still the same idea of taking a derivative, setting it equal to 0 and finding those critical points. All right, I'll really stop talking. If you didn't, make sure you got the attendance form. If you didn't, it's right up here. There's a pen if you need one. Stop the video. Yeah, what's up?
Keep seeing you like do like a trick to do powers and it's like fraction. What's the trick?
So the trick, I wouldn't say it's a trick